And now we'll pivot slightly to hear from Wim Tiest, who is also an AI professional and a life sciences expert. He is the founder and CTO of CPath, Connected-Pathology. But he likes to say that AI-driven technology is not the future, it is the now. I would like to give the floor to Wim Tiest.
So actually what I would like to do is to give you a little look under the hood of AI and to give you a couple of keys how to get involved with it. I have 15 minutes for that, so I would say start the clock. I'm going to give you some reading keys, what you need to know about AI if you just want to get a general understanding about what's talking here. I also want to talk a little bit about realistic expectations. I think this cleanly tags into the previous and the following presentations we will have today. And I'll use my own field in pathology as a case study just to show you what is possible and how we can get into it. So what are we trying to do? Actually, we're trying to take data and we're trying to get to an interpretation or a classification or prediction. In the old ways, we would actually build a mathematical or a logical model. We would use experts to tap into the knowledge. This model would have a sort of fixed performance once it was built. And the big aim would be actually to reduce uncertainty and to use a lot of statistics so we can be much better in predicting, much better in classifying. With AI, the world is kind of changing. Actually, we still choose a model, but we choose a model based on the capabilities it has, the generic capabilities of the model. Because actually, the model will learn by itself. It will learn from examples. And by doing that, its performance will increase the more we use it. And actually, we're not afraid of uncertainty. Actually, AI is about embracing the uncertainty. We're going to look at error rate, and error rate is actually going to help us to learn. So that's really the big shift. When you talk about statistics, it's about trying to reduce uncertainty and mastering it. AI is trying to exploit uncertainty and turning it into a learning experience. And that's a very different way and a very different mindset of doing projects. Now, choosing a model, what capabilities do I need? Well, there's a lot of choices. There's everyday new publications on new models, new designs, but they all fall in a number of fixed patterns. Actually, when you just want to correlate something complex between data and outputs, and you know it's a non-linear relationship, that's where classical neural networks come into play. If you want to extract patterns, for instance, from images or from time series, that's where the so-called convolutional networks are very strong. If you want to observe interactions between different samples or different observations, for instance, you want to see words in a context of a text, that's where you need some form of recurrence, networks that talk to different parts of the network. And that's where the transformers are not these automobiles transforming into robots, it's a very different thing. But it's a type of network that actually has a lot of interactions inside of the model and can really look back in the past and into the future. And actually, if you have a lot of information and the model needs to be able to focus and to filter out relevant information, you have something called attention mechanisms, which is also something that we do as human. If you show us a complex picture, we will quickly grasp which parts of the picture are important to look at. Well, that's the kind of concept that attention mechanisms try to bring to AI. Now, once you've chosen a model, you have to go work with it. Working with a model in AI is learning. Now, learning, you can again do that in many different ways. The most classical one that you hear about is you get yourself a large series of matched input and output. For instance, I want to recognize dogs or cats. I get a lot of pictures that are labeled dog, cat. I put these into my model. I have a loop going through the model, and each time it sees a new picture, it's going to fine-tune its parameters, and in the end, it's going to become better at recognizing cats. That's a very traditional way of learning. It takes a lot of data, and it takes a lot of labeled data. Another little bit more clever way of learning is what's called reinforcement learning. Actually, these are the mechanisms that are put in place if you want to learn a computer to play a computer game. For instance, Space Invaders is a very classical example. Actually, you just give the computer the controls. You say you can go left and right, you can shoot, you can go up and down. And that's where you need to get. You need to kill enemies. And the computer just experiments and gets rewarded or penalized for good or bad moves. And by doing all these experiments, actually, it learns to perform better. Then there's the adversarial networks, what Mieke already mentioned. Actually, in this kind of learning situation, the computer auto-generates data. So you have one part of the system that is trying to simulate or generate fake data. And you have another part of the system that is trying to distinguish it from real data. And by playing these two systems against each other, they both get better. In the end, you end up with a better truth detector, but unfortunately, you also end up often with a better fake generator, which is sometimes the downside and where you end up with deep fake and deep fake images. One of my favorites actually is unsupervised learning. Why? Because actually you don't rely on experts to label your data. You have your computer, your model itself looking for patterns, looking for learning experiences. For instance, you give it a full text, you take out some words, and you ask the computer to complete the gaps. Actually, the system itself will try to learn what text is, how text fits together, and what words fit best in what places. And it takes very little expert input to actually present data to the system. And there's many other and hybrid ways that exist these days. Now, managing expectation, I think that's probably the most important if you want to get into AI. My point today is that you should see AI today as a companion. Replacing the human expert, that's science fiction. That's certainly not for the next decade. But AI is a good target as a companion, or what you could call an augmented intelligence. It can take away the repetitive work from experts. It can do it in a much less error-prone way. It can definitely increase the span of data the human can grasp. It's very good at searching and recommending across vast amount of data and helping experts to make better decisions. And while doing that, it can learn from the experts. So gradually, there is some maneuvering space of the system getting into more expertise and more help for the expert. The other thing is that AI is like warm water and not reinventing it. Actually, if you want to do models from scratch, it takes massive computing powers. The strong algorithms that you see showcased outside, they are built on millions of data points. They are built by the Googles and Facebooks of this world with unlimited computer power and unlimited energy as well. Actually, as a small company or a company that wants to start in AI, you don't need to do that. Actually, there's a very nice principle in AI that's called transfer learning. Actually, what it does is that it can take an existing model that has been learned on large amounts of data, where actually the data first has been converted into patterns and features of the data, and those features are then used to lead to an output or a decision. And actually, the nice thing is that you can reuse that first layer. You can actually use the part of the model that can extract patterns and features from data and apply it to very different data sets, which means that you only need to train your own specific part, the conclusions that you want to draw from the data. And that still requires data, obviously, still requires some computing power, but it's nothing compared to learning the first step where you need to extract patterns from huge amounts of data. And that's a method that's being used more and more, especially, I would say, in life sciences and in other applications, in image recognition, text recognition, because it really speeds up and lowers the access to the AI community for a lot of users. Also, downside and upside, it's a very rich community of published models. There's still a lot in open source in AI. There's still a lot of models that are being trained and made public, which means that if you want to start into AI, there's a lot of material out there that can be used as a starting point, especially if you want to make good use of it. That's certainly an enormous wealth of resources. Now, typical AI project always starts with defining the problem. Why have I put it here? Because a lot of people believe that they can solve their problem with AI, and it's not the case. And we shouldn't waste our time and effort in trying to do it. So a good problem statement and a very open question, is this something where I can use AI? And then you come down to data. And we'll talk a bit more about data in the next session. But data is key. You need to have it. It needs to be of good quality. You need to have enough of it. And you need to analyze it before you use it. You have to be really sure it's solid. Only then you can start to design your models, train your models, and implement them. But the first steps, I don't think we should ignore it, especially in a very sensitive area like life sciences. If you go on the wrong data set, you will end up in a big mess. And I think a lot of our colleagues have learned that to their shame and to their big expenses. It's not just about starting and quickly going into the model, spend time on the first steps. I think that's one of the clear recommendations I could give. Now, just to wrap it up, a case study. This is something we've been doing ourselves. It also shows that it's perfectly possible as a small company to get into that area. Digital pathology actually is a fairly complex thing because it starts with a lot of technical work on organs and animals. There's colors put on slides. There's digitalization with a scanning microscope. There's very big images being produced. And then there's a lot of expert work that needs to be done by an expert pathologist. And to put this whole flow into a digital flow is a fairly complex project. And AI can play a number of roles into that. The key role AI can play here is as a companion. Actually, we've realized that the expert pathologist, whose time is very valuable and there's not that many of them, they spend a lot of time looking at things where there's nothing to be seen. Actually, the most written conclusion on a pathology report is nothing to report. And actually, that takes probably 80% of their working time is just to check that there's nothing to be seen. Now, today, they do that, and on top of that, they do the real expert work, where their real in-depth knowledge is needed. What we would like to do by using AI is to move the algorithms into this area of this 80%. In the middle, there's still a big gray zone, where today we don't have really the tools. The algorithms do the basic stuff today. They do some quality control and some image processing. Where we really would like to move it is up throughout the 80%. As much as we can recover at that time, the more efficient the expert can be put to using its expertise in doing pathology. On top of it, these physical slides and hardware hinder the remote workflow. So the more digital we can work, the better the gain. Another area for AI here is that there's vast amount of data in unstructured images. We think that AI can help to unlock that data and to make sure that we can find references and examples in others. To illustrate it, this just summarizes where you can go with AI from one single high-definition image. Actually, you can segment images, you can do calculation, for instance, on the yellow structures which are cysts in a kidney. You can make sure that your objects that are on a slide are nicely extracted and presented and are clean. You can identify and classify, for instance, cells in those images. You can look up other images that match certain features and that come from a big database. Or you can link the text in a pathology report back to the features that you observe in the image. And all of these areas somewhere can be covered by different tools within the whole arena of AI. And they all can be implemented with today's technology. And that's actually what we're trying to do with CPAT. And I think that's a nice example to also show what can be done within life sciences in AI. And actually, I think I'm well within my time. I just have my last slide to wrap up. This is the work I'm actually doing within CPAT. But I'm also active in the general field of AI. So if you need any help, any questions, I'm always ready to share the experience of the path that we've gone through ourselves. And with that, I want to thank the organizers and wrap up my talk with that. And have a good afternoon.